Here we are at the outer extremity of the delta, and to my left, the ice sheet from which the delta was built is in there a mile or so, and in this direction was the ocean of the time. And this is the outer edge of the delta. And so the outer edge of the delta, the water was coming from the glacier across the delta to the outer edge and then out into the Atlantic Ocean of the time. So the ocean was at about this level, right in here. This is 250 feet above modern sea level now. All right, but this feature that we're looking at here, this immediate drop-off and then a flat surface, is not the normal outer edge of a delta. If you went to the Nile Delta or the Mississippi Delta at New Orleans, you would see the outer edge of the delta just falls away very gently, maybe an angle of 5 or 6 degrees at the very most, because the sediment coming from the rivers is sliding down. But this is a very abrupt thing. What's happened here is that as the ice pulled back from the margin receded from the back end of the delta, no more water could be contributed to the delta surface from the ice. So the streams stopped running and they stopped discharging stuff out here. Well, what's here then? You got this big sand and gravel deposit standing in the open ocean. That's the open ocean, and you can see it would be open for as far as you can see. The next stop would be southern tip of Nova Scotia or something, or maybe Portugal. But the land level rose a little bit, and the sea level then stopped. So they were together, the land and the sea were together, but the land level went up about 20 feet relative to the ocean level. And I'll come back to this in a minute. And it stayed there. So now we've got waves banging into the front edge of this delta like they do on the outer face of Cape Cod. And they cut a wave-cut cliff and a platform in front of it. This is exactly what you have on the outer edge of Cape Cod. Big cliffs. You put your blanket and your lunch down there, and between you and there's a beach area and then the ocean. On a stormy day, however, the waves might come right up to the edge of this cliff, the little cliff, undercut it, and it would slide down and the cliff would recede along this shoreline. Well, so we have this really fossil shoreline, and this is the cliff, that's the Nick Point, the storm high tide, and then out there, if you walked across it, which we can't do today because of the blueberries, you go over ridge after ridge, and those are beaches. And as the sea level dropped down to its present level, the beaches became abandoned, and this is the surface that we have today. It's identically the same as any wave-cut cliff and beach area along Cape Cod or any other place like this on soft sediment rather than the bedrock type of shoreline that we have along most of the coast of Maine. Now this raises a kind of question. We'll come back to this in a minute, the level changes. But one of the questions you could ask intellectually, when was this cliff made? What time of year did you have the big storms? Well, the immediate reaction is to think of today, and the storms are from the northeast, and they do a lot of damage along the Maine coast in the winter. But now if we look at the marine sediment, the clay that underlies that whole area out there, the ocean bottom, beginning where the trees are, and we take the shells, marine shells out of it, we find out that they're organisms that live in the mid to high Arctic today, central Greenland and northward. Greenlandic scallops, various types of things. Also, whales occasionally are found in this sediment. Walruses, a number of walruses have been found, and they're in the Maine State Museum with the big tusks, and seals and fish and seaweed. And all of this is Arctic. So now, when this shoreline was formed, we're faced with conditions that exist today in central Greenland. And what's central Greenland look like in the ocean in the winter? It's ice. It's frozen ice, frozen ocean. And when you have a frozen ocean, you don't have waves banging against the shore. You have no waves at all. And so it looks like the storms that did this were really in the summertime. And if we ask the question even further, which way did the wind come from that did it? The way to examine this is to look, as the sediment is eroded here, which way did it move? Did it move along the beach in that direction, or did it move along the beach in this direction? So you start looking for evidence of that motion, and along here in general, it moved towards the east as far as I can see, not based on what I see right here. The sediment had a longshore current that went in that direction. That means the waves were coming in from the southwest, like this, and the sediment's moving that way. Well, lo and behold, here we are in July, and what's the wind direction today? It's from the southwest. It's right there. This is the prevailing summer wind in the west in the summer now, and it appears to be the prevailing wind when this delta was built 13,500 years ago, or 15,300 years ago. This is paleoclimate evidence that can be put into numerical models. And if you run the model backwards and ask the question, what were wind directions in the summer 15,300 years ago, it'll spit out a wind direction for you theoretically, if it's a correct model. If it doesn't, then you can fix the model using this kind of field evidence. It's not very detailed, it's not numerical, it's just a generality. So it's this kind of approach that helps us make climate models that fit the past, and if they fit the past properly, then you run them forward as predictive models for the future. Just a little bit of information on how those things are done. This marine cut cliff can be traced roughly at the same elevation from St. John, New Brunswick down into central Maine at least. So the cliff, the sea level was more or less constant, not always everywhere, but pretty constant at about 250 feet above modern level at the year, around the year 15,300. So it's a very traceable thing. Trace it back to the delta at Franklin, you can trace it back to the delta in Ellsworth, and beyond to the southwest, and you find the same shorelines. So it's something that's traceable. But it reflects a time when the ice margin has pulled back, no more sediment, the land comes up a little bit, and the sea attacks it in the summertime. So that's the whole story there. A little bit about land level and sea level change while we're standing here. If you put ice on the landscape, the weight of the ice pushes the landscape down. For example, if you have three miles of ice, the land surface, granite and all, would go down about 1 mile. If you take the ice away, the land level comes up 1 mile. All right, so now we have ice over this area. The ice was out on the continental shelf at 20,000 years ago, and there was about 2 miles of ice right here, vertically up. And so the land level went down one third of that distance. And you take away the ice, and the land level then comes back up. So that's one thing that's happening. The other, and it's happening while the ice thins. So as the ice thins, it's coming up all the time, but you can't record that. You just know it's happening. When the ice moves away and the land continues, and you've got a shoreline on that land, the shoreline then goes up and you can measure that. At the same time, you got ice from here to the north end of Canada, and that's melting and going back into the ocean. So the ocean level is going up. When the glaciers were at their full-bodied stage, and terminated at the outer edge of the continental shelf here, and in Scandinavia the same way, so forth. Sea level around the world was 300 feet lower than it is today. And so by putting the ocean water back into the ocean, sea level comes up. And I have this diagram. This is a funny little diagram, but it gives you the idea, and you can think about this. Very crude diagram. But if we assume that, let's look at this side of it, and here's the present level of the sea. And if we go to the graphs that talk about sea level levels and time in the post-glacial kind of sense, if we ask the diagram where sea level was at 13,500, then it's minus 200 feet. All right. This is the wrong figure. This is radiocarbon dates. I'll have to go back to that. But when the delta was formed, this is the delta form, should be 15,300 on your map. But sea level was 200 feet lower than it is today. Now let's go over here. And so on this diagram, sea level has come from minus 200 feet up to the present since 13,000, I'll use this figure, 13,500, delta time. We go over to the delta. In order to form the delta 13,500 years ago, you had to have it equally depressed with the ocean. So the ocean is down 200 feet. So the land surface, this delta had to be down at 200 feet also. So the ocean and delta were together. Now, as time went on, the land has come up to there, where it is today. It's come up 200 feet. The delta has come up 200 feet plus 250 feet. Got a measurable land level rise of 450 feet, if you think about it. And a lot of the uplift of the land took place under the ice, so we don't see a lot of it, but we can actually measure this land level change here by simply analyzing the delta, knowing the age of the delta and the sea levels. So, in a very simple way, we can understand that the land levels and sea levels do this. You know, land goes down, goes up, sea levels go down and up. That's the way it works. So the question is to make it work to fit the geology, and that's what we just did.